Hello Math 2413 students, here's lesson 10, further applications of differential calculus. Here in lesson 10, we're going to study various leftover topics on applications of the derivatives. The structure is rather miscellaneous. So far in every lesson, we had some central theme and flow of logic. No such thing here. Here in lesson 10, every section is on its own, and some of them have been covered before. Consider those as reviews. Okay, let's begin. Lesson 1, Section 1, L'Hopital's rule. And it is a useful rule for limit computation. It's a little bit hard to read, so let me expand the font. Okay. It works for 0 over 0 type, or infinity over infinity type limit, and the limit of the fraction f over g is the limit of the fractions of the derivatives f prime over g prime. If the latter is simpler, go ahead, and maybe we'll have to do this several times. Let's go with an example problem. As a matter of fact, I better keep larger font. Yeah, we have a lot of fractions here and some superscripts as well, so let's keep it like that. Okay, we have this problem, and please check whether this is 0 over 0 type or infinity over infinity type. So if you plug in x equal to 0, what is this? Secant of 0 is 1. So numerator is 1 minus 1, and the denominator is 0. Yes, this is 0 over 0 type limit. So we can apply L'Hopital's rule. We can take the derivatives, and here we go. Let's copy and paste this expression, and let's take the derivative. The derivative of secant, what is it? That's secant times tangent. And the derivative of the constant 1, that's 0, of course. In the denominator, we get like this. Of course, nobody writes like this. Minus 0, let's get it off. On second thought, no, let's just keep that. And then let's plug in x equal to 0. What do we get? Secant of 0, what is secant of 0? Secant of 0 is 1. Tangent of 0 is 0, so this is 0 times 1, so the answer is 0. So what do we have here as an answer key? Yes, the very same computation and the same answer. I don't need this anymore. Okay, how about the next problem? This is clearly an infinity over infinity type problem. Plug in infinity to the numerator, we have infinity squared, okay, that goes to infinity, and exponential squared, that too goes to infinity. So let's apply L'Hopital's rule, take the derivatives, the numerator becomes 2x plus 1, and the denominator stays as e to the x because exponential function stays all the same time. And we got another infinity over infinity type limit, but compare that with the previous version. It's a little bit better. You see, second degree, now first degree. So there's an improvement. Let's do this again. Take the derivatives again, and the numerator now goes down to a constant, 2. Denominator, natural exponential stay the same, so we get that, and this is not infinity over infinity type anymore. It is finite over infinity type limit, so that's 0. Here's the answer key, and yes, indeed, the very same problem, very same computation. Let's keep this here. Okay, last problem here. How about this? This looks a bit complicated. And is this indeed a 0 over 0 type or infinity over infinity type? please check. Please check your computation. Is this a 0 over 0 type or an infinity over infinity type problem? Want to check? Okay, let's go ahead and check. So this is pi over 3 here, and then pi over 3 here. And then, what is cosine of pi over 3? Cosine of pi over 3 is 1/2. So this entire thing in the numerator is 2 times 1/2 minus 1. So it's 1 minus 1. How about the denominator here? Sine of pi over 3. What is sine of pi over 3? That's square root of 3 over 2. And then don't forget square here. So yeah, you have to take square. And then if you simplify, let's see, the numerator, 2 times 1/2, 1 minus 1. And how about the denominator here? Let's see, this thing squared, so 4 times 3/4 minus 3. So this entire thing is again 3 minus 3. So yes, we have 0 over 0 types. Okay, all right. We checked whether those are in correct type or not. If it is not a correct type, then it may be a trivial limit. It may be something else. And that's one of the important steps to avoid a L'Hopital's rule mistake. If you just blindly take the derivatives and apply L'Hopital's rule for other types, then things may not work out. So make sure you check whether this is 0 over 0 type or infinity over infinity type, and we just checked. It's 0 over 0 type. Now let's take the derivative. Numerator is going to be simple. Derivative of cosine is negative sine. So that's what you're going to get in the numerator. And of course, constant becomes 0, so that's what you get. How about the denominator? It's pretty simple to have this minus 0 because that's constant. This part is going to be a bit of a problem. How do you take the derivative of this 4 sine squared of x, as I just highlighted? Well, please recall that sine squared here is, as a matter of fact, sine of x squared. You see, this sine squared is actually sine of x squared. So the outer function is not sine, the outer function is second power function. So you can apply the chain rule accordingly. 4 times 2 is 8, and then inside never changes. And then you have to multiply the derivative of the inside. So that's the derivative computation here associated to this sine squared part. Well, I should have included the coefficient as well. Okay, satisfied? All right, let's go ahead with some simplification here. And I don't need this red color anymore. Let's see, minus 0, that's unnecessary, of course. And sine of x and this sine of x will cancel each other off. And then 2 over 8, I can rewrite as 1 over 4. Okay, what is this? Negative 1 over 4, and then what is cosine of pi over 3? That's 1/2. So we get conclusion. 4 times 1/2 is just 2, so we're going to get 1/2. And don't forget the negative sign. So the last problem was definitely harder. We can use L'Hopital's rule, take the derivative of the numerator and take the derivative of the denominator separately. And when you take the derivative of the denominator, beware of the chain rule because we have sine squared function here. So tougher derivative computation, but it's a derivative anyway. And of course, make sure you check whether this is 0 over 0 type or infinity over infinity type at this step 1, because it may be something else. L'Hopital's rule does not work for other kinds of limits. Here's the answer key and the very same computation. You can see that. This one looks a little bit better with color coding. Okay, so much for 1.2. Now, do we have enough time for some 1.3 types of problem? 0 times infinity type limits. I think we'll have enough time for at least one problem, so let's go ahead and do that. And let's take a little bit bigger font again. We're going to need fraction again. So this is 0 times infinity type limits. This one goes to infinity, yes? This one goes to 0. E to the negative infinity. It's not a fraction, but we can manipulate it so that it becomes a fraction like this. You can put this, oops, sorry about the typo. And let's see, put some space here. Okay, that looks a little bit better. So this one is clearly an infinity over infinity type limit that we studied already. Same as this, remember? Even if you forgot, you can just go ahead with the L'Hopital's rule computation. Take the derivative here, we have 2x plus 1. And the denominator stays the same, of course. It's a natural exponential function. And then once more, because this is again an infinity over infinity type limit, so we have 2 over exponential, 2 over infinity, so that's 0. So you can change this 0 times infinity type into infinity over infinity type, and then you can go ahead. So change it to fraction, and then you can use L'Hopital's rule. Now, do I have enough time for the next problems? Probably not, so let's just stop here. And we'll defer the other problems in the next video. We'll stop here. See you soon.